Hello, welcome. My name is Saikat Guha, and my pleasure to welcome you today to the Optical Sciences Colloquium. It's a real pleasure and privilege to introduce my close colleague and friend, Zheshen Zhang. He's an assistant professor in the Material Science and Engineering Department here at UFA. Zheshen started here about a year ago, same time that I started at UFA. And Zheshen is an expert in quantum optics in various areas of applications of quantum photonics and quantum light in applications in communication security, to sensing, to a variety of different problems in imaging and metrology. Zheshen did his PhD in 2011, I believe, from Georgia Institute of Technology in their Electrical and Computer Engineering Department, after which he went to MIT as a postdoc with Jeff Shapiro and Franco Wong's group at the Research Lab of Electronics. After that, he got promoted to being a research scientist in 2015 at MIT. During the time, he did an experiment that still holds the record of the highest data rate on a quantum key distribution experiment done over free space. So right now, Zheshen leads a group at the MSc department. He has a joint affiliation with the Optical Sciences department, and he's doing experiments in entanglement-assisted sensing, on quantum secured communications, and quantum imaging. So Zheshen is going to tell us today about his work on entanglement-assisted quantum sensing and communications.
Yeah, thank you very much, Saika. And from Saika's introduction, you probably already observed that we're actually from the same family, right, at MIT. So, and actually right now we still have a lot of very close collaborations on a number of different projects, which I'm going to briefly give a brief overview of this project in the second part of my talk. But the first part of my talk would be primarily based on my postdoc work, which was performed in Jeff Shapiro and Franco Wong's group at MIT. So there, I was involved in multiple projects, including using entanglement to improve the sensitivity of a measurement system, or people also call it quantum-enhanced sensing, and also to build broadband quantum communication systems. So I'm going to just overview these projects and the main result. But before getting into the work that I did, so let's just give a very high-level overview of this so-called quantum-enabled technology, or some people call it the second quantum revolution, or quantum 2.0. So, in essence, if you talk about quantum mechanics, or if you try to discriminate quantum and classical, we can think about, everything is quantum. Okay, so everything can be described by the laws of quantum mechanics. Okay, but the difference for this quantum-enabled technology is that you can actually leverage some of the quantum mechanical phenomena, such as entanglement and the superposition principle, at a macroscopic level. So it's fundamentally different than these devices like lasers or CCD cameras. They are all based on quantum mechanical principles, but only at a microscopic level. Okay, so which means, these electrons or these semiconductor band gap structures can be described by quantum mechanical laws, but when you use them, you actually don't observe any quantum mechanical phenomena. Okay, but here what we are trying to do is very different. The so-called quantum-enabled technology is actually you try to take advantage of these quantum mechanical phenomena like entanglement at a macroscopic level, and by doing so, you would be able to build ultra-precise sensors, which is going to be one topic of this talk here. How do you utilize entangled photons to increase the sensitivity of measurements? Or you can rely on this so-called quantum no-cloning theorem to build a communication system that can never be cracked by any present or future technologies. Okay. And in the bottom panel, you see the two different applications, which is one is the quantum simulation, and the other one is quantum computing. A lot of people think they are, of the same idea. So the idea is that you use quantum mechanical phenomena to speed up the processing of solving a particular problem, so that this problem can be effectively solved by quantum computing, but it cannot be solved by any classical means. Okay, but if you put this whole thing into a bigger picture, so like all these classical technologies, this quantum technology can also be divided into different levels of research or different layers of research. So at the very fundamental level, you have this material research. You try to find either quantum materials with a bigger nonlinearity, or you try to find quantum materials with a longer coherence time to build the qubit in your quantum computer. And once you have these fundamental renovations in materials, you can put them together to build platforms, and the platform is going to comprise of, for example, superconducting circuits, or more recently, we're also working on these integrated quantum photonic devices, or these conventional tabletop quantum optics setups. And then we talk about using these platforms to build systems and applications. And the three applications we have already discussed are sensing, imaging, secure communication, and physical simulation and computing. Okay. So in this talk, it basically consists of two parts. Okay, so part one is going to be focused on quantum-enhanced sensing, or we have a different name for it. It's called quantum illumination. So essentially, how you use entanglement produced by nonlinear optics to improve the sensitivity of measurement. Okay, and we're also going to talk about some theory work about how you build a optimal quantum receiver to attain the ultimate quantum limit predicted by quantum information theory. Okay? And the second part will be dedicated to quantum secure communication. So it's an idea using the fundamental laws of quantum mechanics to protect the integrity of your communication, to make sure that your transmitted data cannot be cracked by any future or present technology. Okay? So now let's get into the first part first. So let's talk about sensing. Okay? But before we actually get into quantum-enhanced sensing, I'm just giving a very simple example of a classical sensing problem. Okay? So as you see here, it's actually a target detection problem. So in this problem, okay, so you have a target, okay, which can be potentially embedded in a very lossy and noisy environment. And your objective is to interrogate either the presence or absence of this target. Okay? And to do so, you're going to use a classical transmitter. So here is just a very simple laser. Okay? You produce a pulse, okay? And you shoot the pulse towards the potential location of this target. Okay? If the target is present, okay, as in the case, a top panel, okay, what you're going to have at the receiver, which is a classical receiver, is that you're going to have a very small portion of the original signal coming back to your receiver. This is because the environment is highly lossy, and the reflectivity of the target is also very low. Okay, but in the meantime, what you're going to have is a very bright noise background, so that your returned, this tiny piece of signal, is embedded in this very bright noise background. Okay, so this is the target present case. And if the target is absent, okay, so you still have a probe, you try to shoot your target, but because the target is absent, there's nothing reflected back from the target. So all you have at the receiver is noise background. Okay. So now your goal is to make a discrimination between these two cases. Okay, so you're trying to tell if the target is present or absent, okay, by making a measurement from this classical receiver. Okay, so now we have this question. So can you use any quantum mechanical resource to improve the performance of this target detection system? And this quantum mechanical approach is called quantum illumination. So it's a name came up by Theorem when he originally proposed this scheme. Okay? So now you replace this classical laser transmitter with an entanglement transmitter. So you produce entangled probe and a local reference. Okay? So they are entangled. You can think about them as a pair of entangled photons. Okay? So you use the probe to illuminate your target, okay? But you locally retain your reference, which was originally entangled with the probe. Okay? And at the receiver, from the probe part, you still have a tiny piece of signal embedded in a bright noise background. Okay? So in the target absent case, you use your probe to interrogate your target, but nothing comes back from your probe signal, and all you have is noise background, which is uncorrelated with your retained reference. Okay? So here, you indeed have a really bright noise background, so that the background is so strong that the initial entanglement is completely destroyed. Okay? So that means even in the target present case, if you look at the retained reference with your returned signal, so there's no entanglement there. Okay? So can you construct a entanglement transmitter and receiver to show that this entanglement-enhanced quantum illumination target detection actually outperforms the best classical illumination scheme? So this is what we're going to show. Okay? But before that, let's first introduce, entanglement, right? Because when you talk about entanglement, you may naturally ask what entanglement is. Okay, so from science fiction or from some other literatures, you think entanglement might be something quite hard to understand. Einstein described entanglement as spooky action at a distance. Okay, but as you see, in this very simple cartoon, it is really not that magic. Okay, so the way we produce entanglement is actually, in our lab, the entanglement generation process is very simple. Okay? So you just have a nonlinear material or a nonlinear crystal. Okay? You pump the nonlinear crystal with high energy and a high flux pump beam. Okay? So because the crystal is nonlinear, okay, due to the nonlinearity with a small probability, a pump photon, okay, which has high energy, marked in purple, is going to be converted into a pair of photons. Okay? So if in this case, if one photon is blue detuned and the other photon must be red detuned, okay? Because the energy conservation, the sum of their energy should be equal to the original energy of the pump photon. And in the meantime, you also observe that the two photons must be created at the same time. Okay? This is because whenever a pump photon is annihilated, that process is going to create a pair of these converted photon pair. Okay? And likewise, if one photon is red detuned, the other photon must be blue detuned. Okay? And we have all learned this basic quantum mechanics, or being more specific, the Planck law. Okay? The Planck law essentially relates energy with frequency. Okay? So if two photons are anti-correlated in energy, which means they are also anti-correlated in their frequency. So as such, in this process, you see there are two different correlations here. So the two photons, a pair of photons are correlated in their emission time and anti-correlated in their frequency. Right? But if you look at this process more closely, you find that this is a non-classical correlation. But why is that? So it's actually very simple to illustrate. Okay? So imagine, classically, I let you produce a pair of photons, and the two photons are completely overlapping in their emission time. Okay, so which means the temporal profile of each photon is very narrow. Okay, so that they completely lined up in their emission time. Okay, so then if you look at their frequency domain representation, okay, the spectrum of each pulse is actually very broad, right? So if you have operate a ultra fast laser, the narrower the pulse width is, the broader its spectrum is going to be. So what this implies is that if you try to make a measurement to determine the frequency of one photon, this frequency is going to be random across this whole area, and likewise, if you're going to determine the frequency of your second photon, it's going to be random across this whole region. Okay. Therefore, there is no spectral correlation between the two photons. Okay. So now you think about, what about we create two photons that the two photons share the same frequency. Okay. So what is this situation? You just use two narrowband lasers. Okay. So you just completely correlate the color or the wavelength of the two lasers so that the photons emitted from the two lasers are completely correlated in their frequency. And now, because you have a CW system, you have a CW laser, you don't have any control of the emission time of each photon. So that means the two photons are completely uncorrelated in their emission time. Okay? So as such, the sort of correlation you have seen here in the top panel, correlations in both time and anti-correlation in frequency is a non-classical signature. Okay? So which means the two photons are entangled. Okay, so now you can think about, we can use, one photon, or one arm of the photon to serve as a probe, and the other arm of the photon to serve as a reference that you can locally retain. Okay, so that by virtue of their tight correlation, you might be able to improve the sensitivity of your target detection, quantum illumination target detection scheme. Okay. But nonetheless, you still need to build a receiver for that. So actually, the receiver idea originally was proposed by Saika and his colleague Barris Ackerman in a theoretical proposal back in 2009. So the idea is that you use a second nonlinear process to build this quantum receiver. Okay. So now let's just first look at this target absent case. So now you have a radar return, which is basically noise. Okay, and you have your locally retained reference. It's not correlated with noise, and once the two beams go through this nonlinear process, not much would happen because noise does not interact very well with your reference arm. What you observe is just a small portion of the noise is going to be converted onto your locally retained reference. Okay, then you just perform a measurement on the reference. Okay, but nonetheless, if the target is present, okay, so you have a tiny bit of signal embedded in this noise background. Okay, it is this tiny bit of signal that actually changed the game. Okay, so once the signal, the returned signal, and the retained reference go through this nonlinear process, the residue probe is actually going to locate this locally retained reference automatically, and each of them would receive a gain from this nonlinear process, so that your output reference arm from this nonlinear process is going to be amplified. Okay, so this signal is going to be stronger than this signal. Okay? So now, just by simply measuring the intensity from your nonlinear process, you would be able to interrogate if the target is absent or present. So it's just a very simple, nonlinear process, which would allow you to do this state discrimination. Okay, so if we put this in a more rigorous, form, this is entanglement source, which I'm probably not gonna go through the details, but this entanglement source is very broadband, and each mode pair can be described by this superposition of photon pair states, so which more technically we call it a two-mode squeeze state, and the entanglement mathematically can be quantified by this phase correlation between the signal and the idler, or the probe and the reference. Okay? And in the quantum regime, this correlation is much stronger than any classical system would be able to afford, so that you get a entanglement-enhanced performance. Okay? And for the quantum receiver, which we call this optical parametric amplifier receiver, okay, it's the same. Okay? So when you have a target present case, there's a residue correlation between your return signal and your local reference, which we also call idler. And because of this correlation, okay, and this both arms would be amplified. Okay. And if you just do some more math, you would find if you derive the signal-to-noise ratio for this quantum illumination target detection versus the classical illumination target detection, the signal-to-noise ratio for this quantum case is a factor of 2 or 3 dB higher than the best classical scheme that you can build. Okay. But there's a caveat here. The caveat is that here we assume there's no experimental non-ideality. But in an experiment, we do have this experimental non-ideality. So we don't get this 3 dB, we get about 1 dB, as you will see in our subsequent slides. Okay. So, but this slide is just for some of the like Saika expert and or Christos, Gaussic, you're very familiar with this, Gaussian quantum information. So this slide is just for you guys. Okay. Okay. So more technically, what you are doing here is that if you think about this returned probe and your returned reference describe them in a covariance matrix. Okay. So this cross term. Okay, this diagonal term is almost the same in the case of targets present or absent. Okay, but the major difference is this anti-diagonal term, which describes the correlation between the signal and idler. Okay, so once you have an anti-diagonal term is non-zero, which means your target would be present. If it is 0, then your target is absent. Okay, so this is, more technically, you can think about this target detection problem from this perspective. Okay, so now let's come back to the experiment, which this slide is for most people in this room. Okay, so you have quantum illumination experiment. You have an entanglement transmitter, which is going to produce entangled probe and the reference, and your probe would interrogate the target. But in the meantime, you have noise injected by your environment. When it comes back, you combine the probe with your returned reference, and further with a pump, and go through a second nonlinear process, which serves as a quantum receiver. And you just filter out all the other light, and you only perform measurement on this reference arm. And this is a more complete experiment, which I'm not going to go through the details. Okay, but this is our measurement. So we perform the SNR measurement in log scale, and this red curve is your signal-to-noise ratio for quantum illumination. And the dashed blue curve is the classical limit. So you actually see, with all the experimental non-idealities, the quantum limit the quantum performance beats the classical limit by about a dB. Okay, and remarkably, this result was obtained in an environment with very large loss, 14 dB loss, and the noise background is actually 75 dB more intense than the signal you send. Okay, so which means the majority of the photon you receive would just be this noise background. And even in this case, you get this quantum enhancement enabled by entanglement. Okay. So now we have talked about this, this OPA receiver, which was proposed by Saika and colleagues. So it's a very nice scheme because it's experimentally very feasible, as we have already built this experiment, but unfortunately, it does not saturate the ultimate quantum limit. Okay. Because from quantum estimation theory, you can derive that the ultimate performance gain for this quantum illumination is 6 dB superior to classical illumination. Okay. But this OPA receiver, which is the receiver we discussed, only allows you to achieve a 3 dB improvement. So you are almost halfway between classical and the optimal quantum quantum performance. And we were asking ourselves, where did the rest 3 dB go? Okay, and we thought we got the answer, and the answer is that if the target is absent, okay, the reference and your return signal go through this nonlinear process, okay, but this process is going to create some correlation between your output reference and your output signal arm. Okay, although initially there's no correlation because the target is absent, but at the output of this receiver, correlation is created. Okay, but for the target absent case, for the target present case, okay, both arms are amplified, but the correlation between the two is also amplified. Okay, so now you just perform a direct detection on your reference arm, and you just completely discard this correlation between the two arms. So you are not detecting the correlation, but actually the correlation actually encode some sort of information, because you see this correlation is stronger than the other correlation. You're not detecting this part. That's why you don't get all the way to the ultimate quantum limit. Okay. So now our question is, how do we actually can completely detect this correlation, or how do we build an optimal receiver for this quantum illumination target detection problem? Okay. So first, like all other work, or it's a very typical scientific discovery process. We just came up with a hypothesis. Okay. So the hypothesis we came up with was just a Hamiltonian. Okay. So this is, if you look at this Hamiltonian, it describes the interaction between three modes. Okay. So the B is a ancillary mode, and this A S A I are the signal and your local reference mode. And if you look closely, this is a some frequency generation Hamiltonian. Okay. So what does this Hamiltonian give you? So why would we come up with this Hamiltonian? Okay. So now we look at this term. Okay. So this term ASAI is, in the mean field approximation, this is actually this phase-sensitive cross-correlation. This describes the correlation between the signal and your local reference. Okay. And if the target is absent, okay, which means this term is going to be 0, okay, then nothing is going to happen, okay, because you have a 0 Hamiltonian, so you don't have any evolution. Okay. But if the target is present, this term becomes non-zero. Okay. So now you can imagine, if you apply this Hamiltonian to this system, you're going to have coherent conversion between the photons in these two modes and the photon in the ancillary mode. So now, if you detect the photon in the ancillary mode, you would be able to determine how much correlation that was present in the signal and the reference return. Okay. So this is how we came up with this hypothesis, this Hamiltonian. So if this correlation is 0, Hamiltonian does nothing. If it is not 0, it would perform coherent conversion between the three modes. So the next thing is like the Qingtao Zhang, so who was a student with Jeff Shapiro and who will be joining the EC department in January, become a new assistant professor here. So he did a simulation. Okay. So what he found was, indeed, it agreed with our intuition behind this Hamiltonian. Okay. So here, if your reference mean photon number is much less than 1, okay, and these two arms has mean photon number much less than 1, but if there is a correlation, okay, now you have coherent conversion of this correlation, okay, with a photon number in this ancillary mode. So at the output of this process, you end up with no correlation, but you end up with photons in this ancillary mode. Okay? Okay. But this only applies if the two modes, the two input modes are weak. Okay? But in our situation, you have very strong case, right? Because the return signal from the background is very strong. Okay? So this approximation actually does not work for our quantum illumination situation. But next thing we do is that, okay, so this doesn't work, but you can imagine we just use a tab, okay, to split a small portion from your return signal and combine with your reference and go through this some frequency generation. Now you have some photons stored here, and now the rest of the photons going to the next cycle. So you just do it multiple times, and you can imagine if you do it multiple times, you would be able to get to the quantum limit by measuring photons in this ancillary mode. Okay, so we're very excited about it, but we did all the calculations, but then we found out was the performance of this receiver is exactly the same as the OPA receiver. So it's still at the 3 dB limit. And then we came back, we asked, okay, why was that? Okay, so we just thought about this problem for a few weeks, then we came up with the answer. Okay. The answer is that by converting this correlation to this photon, okay, you need to conserve energy. Okay? So which means the output photon number from this mode is smaller than the photon number at the input. Okay? And the decrease in the photon number was not detected in this case. Okay, so that's why, there's essentially half of the information you are not detecting. So then we further augment this receiver with another beam splitter at the output and interfere with this untapped portion. Now you find that this measurement, this ancillary mode has exactly the same photon number as the other ancillary mode. So now you get this half of your information back. And if you detect both modes, and our calculation shows that it saturates the ultimate quantum limit. So now you can do more tricks, which I'm not going to introduce, just introduce some feedback mechanism to your scheme, which would further improve the performance. But this is the performance of this so-called quantum-illumination optimal receiver. So this curve is your ultimate quantum limit, and the simulation, which was Monte Carlo simulation, agrees very well with this ultimate quantum limit. And it beats the Chernoff bound. So these blue dots are the receiver without feedback, and the blue dots, the red dots represent the result with this feedback mechanism. So it improves upon this blue dots. But they all beat the performance of this OPA, optical parametric amplification receiver. So this is, for sensing, for this quantum sensing, people have already applied that in gravitational wave detection. And this can also be useful for biosensing. For example, you want to reduce the illumination power so that your sample won't be damaged. It is also called non-invasive imaging. And you can improve the position of your clocks and apply that in microscopy, for example. So that's the first part of my talk. It was about quantum sensing. But now let's talk about quantum communication, which is another major application of this second quantum revolution, or quantum 2.0. So now let's first introduce the very fundamental concept of the quantum no-cloning theorem. So what does it say? So consider you have a quantum emitter. So what is a quantum emitter? The quantum emitter is a device that only emits one and only one photon. Only this is one photon. But let's assume this photon carries a random quantum state. So in this case, it's the vibrational state of this photon, which is a polarization. So let's say if you are given the best cloning machine that nature allows you to build, and you try to duplicate this unknown quantum state carried on this photon. So this is your cloning machine. You you want to duplicate that state, And the no-cloning theorem essentially states that you won't be able to get two perfect copies. So here you get two copies, but they are all distorted from your original state. So this is the no-cloning theorem. You just cannot get two perfect copies. So now you can imagine, you just leverage the no-cloning theorem and apply that to build a quantum secure communication system. So this is what you do. So imagine Alice wants to send a bit of information securely to Bob through a channel that is completely monitored and manipulated by an eavesdropper, Eve. So what Alice will do is that she's going to encode that information, that classical information, into a polarization state of the photon and send that photon through this channel. If Eve wants to know what that state is, she must duplicate a copy of that state. So, but the no-cloning theorem prevents Eve from getting two perfect copies without introducing distortion. Here you see, Eve would get two copies. She retains one and sends the other one to Bob, but both copies are distorted from the original state, so that when Bob receives all the photons sent from Alice, Bob can pick a small portion of these photons and talk to Alice, what was the state you sent, and this was the state that I received. If they don't agree, then that means somebody has looked at the photons, looked at, made a copy. So in that case, Eve's intrusion is going to be unveiled just by this reconciliation between Alice and Bob. Okay, so that's the basic idea of quantum secure communication. Okay, so now you can imagine. Okay, so Alice can just send a classical bit and encode them into quantum state and send to Bob through this channel, and Bob can do decoding and also to monitor the intrusion of an eavesdropper, and Alice just keep doing that. Sending a different quantum state and send through the channel. But unfortunately, in a practical situation, okay, the channel always comes with a significant amount of loss. Right? If you talk about optical communication, loss is about 10 dB per every 50 kilometers of transmission. Okay? So that this photon doesn't get to Bob. Okay? So Alice needs to redo it, okay? And until Alice and Bob share a sufficient number of photons so that they can build a random key out of these received photons. But nonetheless, due to the channel loss, the rate is significantly limited, okay, by channel loss. Okay. But however, due to this appealing feature of providing a ultimate solution to this security problem, because your security is fundamentally guaranteed by the laws of physics rather than any assumptions. Okay? So this actually spurred a global quantum communication race. For example, China sent this satellite to perform ground to space quantum communication, including this quantum key distribution and also quantum teleportation. Okay? And Germany and the UK, they are pursuing research and engineering along the same direction. Okay. So, but as we introduced, the rate of quantum communication is really low. Okay. So actually, the over a channel of about 10 dB loss, the rate is lower than 10 megabit per second, okay, due to loss on single photons. Okay. So this 10 megabit per second, it was demonstrated in labs, and in practice, for example, for that China's quantum communication backbone, the rate was only 8 kilobit per second. So this is really not that appealing compared to classical communication, although this one is more secure than classical case, but the rate is too low. Okay. So we need to come up with an approach to significantly improve the rate of quantum communication. Otherwise, this technology would not be appealing. Okay. So we need to mitigate loss in quantum communication. So what is the solution? But then we first look at, in classical communication, we also have the same problem, right? So because the channel is, regardless it's quantum communication or classical communication, you always need a channel. Okay? And whenever you have a channel, you have loss. Okay? And in classical communication, you also have loss. Okay? But how does classical communication mitigate loss? The idea is actually very simple. Okay? So just don't encode information on a single photon. You use so many photons to encode one bit of information, and during the transmission, even some of the photons are scattered or absorbed by the channel. Bob is still guaranteed to receive enough number of photons so that he can perform reliable decoding. So that's how classical communication mitigates loss. But unfortunately, this approach cannot be used in quantum communication because it is not protected by no cloning theorem. Okay? Just to illustrate, the cloning, if you have so many photons carrying the same quantum state, the cloning is very simple. So the eavesdropper just splits off one photon, okay, which carries exactly the same quantum state as all the photons that Bob received, so that the security is completely broken, okay, because Eve is able to duplicate the state of these photons without introducing any disturbance. So now let's just look at this no cloning theorem. What the no cloning theorem states is that if you have one photon carrying a unknown quantum state, you can't duplicate the state of that photon. Okay? But now imagine, over a bit duration, you have two photons, but the two photons carry different quantum states. You cannot duplicate the state of either photon. Okay, so now if you have a lot of photons within 1 bit duration, and if they all carry random states, you won't be able to copy a state, the state carried by any of the photons. Okay. Okay. So it seems that we have an idea to mitigate loss in quantum communication. Okay. We just, over 1 bit duration, we have multiple photons and let these photons all carry different quantum states. Okay. But there are 2 remaining questions to be tackled. Okay. And the 2 questions is, first, how do you produce so many photons and they all carry different quantum states? Okay. How do you do that? So what device would you use? Okay. So we know if you want to create a lot of photons and they all carry the same state, you just use a laser. Okay. And why do you use a laser? Because a laser is a coherent device. It's a narrowband coherent device so that it would produce a lot of photons, and all these photons would carry exactly the same quantum state. Okay. So now you want all the photons to carry different quantum states, so you must use an incoherent broadband source. Okay. So what is an incoherent broadband source? Black body radiation, right? Or this, just our natural light is a broadband source, or your unseeded optical amplifier. Okay. So this is what we do here. Alice take a incoherent source, okay, to emit photons with random states, okay. But nonetheless, okay, there's no information encoded in this stage, right? So in the classical case, you have all photons carry the same information to encode 1 bit, but here, since all photons carry different bits, different states, how do you encode your information? Okay. And the idea here is that instead of doing a one-way communication system in which Alice just sends information to Bob, you implement a two-way communication system. Okay. So Alice produces broadband photons, send these photons to Bob. At this moment, all the photons don't actually carry any information. Okay. And the information is encoded by Bob. Bob either does nothing to all photons to encode bit 0, or Bob just completely flips the phase of all photons to encode bit 1. Okay. So then Bob introduced some amplification to overcome channel loss and send back. And here, Alice actually retains a very strong and very good reference to decode Bob's encoding. Okay. So now let's consider there's an eavesdropper. There's an eavesdropper. Okay. So eavesdropper can collect all the scattered light from the channel. Okay. So Eve just captures all the lost photons from the channel and tries to infer Bob's encoded information. Okay. So here, because Alice send state is very weak, okay, compared to this reference, okay, Alice retains. Okay. So Eve has no means of faithfully duplicate this Alice reference because this is prevented by the no cloning theorem. Okay. So here you can actually see that because Alice has a very good reference to decode Bob's information, and Eve does not have a good reference to decode Bob's information, so that Alice's performance is much better than Eve's performance. So this is provided by no cloning. But nonetheless, Eve can duplicate exactly what Alice does. Right? Because Eve can have his own reference and generate her own signal and inject to Bob's terminal. Bob encodes and returns. Now Eve can use her own good reference to decode Bob's message, and in this case, there's still no security. Okay, so we need to come up with an approach to mitigate that attack, and the approach we came up with is by using this non-classical feature of photons. Okay. So in addition to this broadband source, Alice also has a entangled photon source, which is used to monitor the security of the system. Okay. So this source is going to produce correlated reference and probe photons, which means whenever a reference photon is generated, you're going to observe a probe photon. And Alice just mix these light with the light the other incoherent light transmitted to Bob. And before Bob does the encoding, Bob is going to tap a very small percentage of the light, okay, and just count the arrival time of these photons with Alice. Okay. And from this simple cartoon, you can already see that only this green curve, okay, the photons in this green curve is going to be arriving at the same time as Alice's reference photon because they come from the same quantum photon pair source. And anything Eve injected is not going to be correlated with Alice's reference because they come from a different source. Okay. So just by measuring the coincidence rate, okay, just by measuring, if their Alice and Bob's photon arrive at the same time, they can rule out Eve's active injection. And more quantitatively, they would actually measure the fraction of Eve's injected light at Bob's terminal. Okay, so we did the experiment. We have a broadband source, which is just this urban doped fiber amplifier, which is combined with this photon pair source, which is a quantum source, and sends the light to Bob, and Bob taps a small percentage to do coincidence counting with Alice, just to count the arrival time of the photons, and Bob does the encoding and send the light back to Alice, and Alice implements a broadband homodyne receiver to decode the message. And from the experimental measurement, you can see, the red curve is Bob's encoded signal, and the blue curve is Alice's decoded signal. You see the zeros and the ones are very well discriminated, so which means you have very good error probability between Alice and Bob. And actually, our error probability agrees very well with our theoretical model. Okay. Now let's come back to this intrusion monitoring. So how would Alice and Bob know that somebody is actually intruding? Okay. So the way, as I introduced, they would just perform this coincidence measurement. Okay. So actually, in our experiment, we implemented a Eve, or we emulated a Eve, and Eve is trying to inject her own light into Bob's terminal, trying to decode Bob's message. But as a first step, we just completely shut down Eve's input so that everything Bob receives comes from Alice. And from this coincidence measurement histogram, you see a peak, which means Alice and Bob's received photons fall into this peak. Okay, so this is, they arrive in this sharp peak. So now, Eve just completely cuts the light from Alice and only injects her own light into Bob, and as you see, that peak disappeared. So that the absence of that peak, so this is our former case, you see a peak here, but if Bob's received light comes from an eavesdropper, the peak is not there, it disappeared, so the absence of the peak actually unveils Eve's intrusion. Okay? But as a smart Eve, she would choose to inject some of her signal and combine that, mix that with Alice's signal and inject them all together to Bob. Okay? And in this case, even in that case, our channel monitor can actually quantify how much light, in terms of the portion in Bob's, all the light Bob receives, how much light comes from Alice and how much light from Eve, and from that parameter, we can use quantum information theory to derive the key rate. Okay. And here, okay, because we have this really broadband encoding, and we are actually able to encode multiple photons into 1 bit. So with a 7 gigabit per second modulation, we can achieve about 1.3 gigabit per second quantum key generation over a channel with 10 dB loss. Okay. So those are the experimental results that Saika collected. Those are the experimental results from all prior experimental quantum key distribution implementations. Okay, so those are the rate versus loss. Okay, and our experiment is about here, so which is about 2 orders of magnitude higher than what other people have achieved. Okay, because we have this really broadband encoding and multiple photons per bit transmission to mitigate channel loss, and also use the quantum light source to verify the security of our system. So right now, so here is just a quantum optics platform. So this is actually a proof of concept quantum illumination target detection experiment, so which is very complicated, but we try to miniaturize that. So this is also one of the topics that is currently being pursued in our lab. And so we try to miniaturize that into a chip, and we also have some ongoing collaboration with Professor Dirk England at MIT. Okay. And the ultimate goal is to put, all the quantum emitters, okay, and the quantum processing units, which can potentially be comprised of these 2D nonlinear materials, and also the detectors all on the same chip. And now you can use a miniaturized quantum platform or quantum information processing platform for multiple applications. For example, we have some ongoing collaboration with with Urs Oettinger in BME. So we try to look at the possibility of using entangled photons to improve the sensitivity or resolution, or to reduce the illuminating power for bioimaging system. And you can also apply that for example, spectroscopy, or to identify the chemical composition of materials. So this is one of the ongoing work, and we are also trying to build a quantum network testbed. So this is just a newly funded project by NSF. It's the NSF Major Research Instrumentation project. So we try to build a quantum network testbed on campus. So that the idea is that we're going to build a few entangled photon sources in a central location in the ECE building, and we're going to pull optical fibers to send the entangled photons to different labs, so that these labs can take advantage of these entangled photons in their own experiment. They can, be working on materials research or imaging work, or we can also train the next generation quantum information science and engineering workforce in these teaching labs. And these labs can in turn, using optical fibers, to access an array of single photon detectors situated in the same location, okay, so that we have this shared facility. And the hope is that we can use entangled photons to indeed entangle different disciplines, okay, so that they can all benefit from this new quantum resources to advance their own field. And this is a topology of this quantum network testbed. So the center is in ECE, and we're going to pull optical fibers to including optical sciences, physics, and this is my building, material science, and the Bio 5 Institute. And we also have some ongoing collaboration with Saika Ivan Georgievich and also General Dynamics. So what we envision is that network testbed would allow us to actually study quantum communication and sensing network at a larger scale. So we're looking at possibilities of, for example, implementing a testbed for this long-haul quantum communication between a geosynchronous satellite and a ground station, to test the feasibility of sending entangled photons with some compensation of this atmospheric turbulence effect over such a long distance. So before concluding, I would like to thank my colleagues, so in particular Saika and NASA Pigambarian. So we have very close collaborations, and also Jennifer, we work on that MRI proposal, and a few other colleagues, and my postdoc supervisor Jeff Shapiro and Franco Wang, my PhD advisor Paul Voss, and our collaborator Mathieu Bloch, and we had some ongoing collaboration with NIST as well. So those are the funding sources. So to summarize, we have talked about quantum sensing and also broadband quantum communication, and we are working on multiple subjects, including building quantum communication networks, quantum sensing, and some photonic quantum processing subjects as well. So thank you very much for your attention, and I would be happy to answer your questions.